The purpose of our lab is to use conservation of energy principles and the conversion of angular velocity to translational velocity in order to validate the coefficients of the moment of inertia that we are provided with as students for a variety of objects. The final velocity of the object and the height at which the object is released will be measured to determine this value.
Our testable question is the K coefficient calculated for our objects using data derived from our experiment the same as the textbook values of the K coefficient for the same objects? Further research on the conservation of energy was necessary to find out what measurements were required to complete the experiment and resulting calculations. Using conservation of energy principles to assume that the total mechanical energy at the top of the incline would be equal to the total mechanical energy at the bottom of the incline, the group set gravitational potential energy at the top of the incline equal to the translational kinetic energy and rotational kinetic energy at the bottom of the ramp. Here are our calculations for our conservation of energy equation. So we set the potential energy of gravity equal to the kinetic energy plus kinetic energy rotational at the bottom of the ramp. Then we inserted the variables for each side of the equation, and we inserted k, or I is equal to k mr squared, where k is the coefficient for the moment of inertia. Next, we inputted the equation v equals rw and applied squares to both sides of the equation. Because they're being multiplied, we can apply it to both sides. In for r squared w squared. So we get the equation mgh equals 1/2 mv squared plus 1/2 k mv squared. Then we divided out the masses since they're on both sides of the equation. Next, we multiply the equation by 2 to remove both the 1/2s to simplify our equation. Our next step would be to divide the velocity out and to attempt to isolate the k value. To complete our equation, we subtracted 1 from this side of the equation to have k all by itself. Our equation was validated by Boston University's website, physics.bu.edu. These were the steps that they had on their website, and here are our steps where we just applied simple mathematical principles to isolate k. In order to find the actual k coefficients for the moment of inertia, the group consulted the internet site dev.physicslab.org. The k coefficient for the moment of inertia found on dev.physicslab.org of a hollow tube is 1. The k coefficient for the moment of inertia of a hollow sphere is 0.667 or 2/3. The k coefficient for the moment of inertia of a solid disk is 0.5. I provided visuals of the objects here. The hollow tube is different from a solid disk in that there is a space in between both sides of the object. A hollow sphere might look solid on the outside, but if cut in half, you would notice that there is a space on the inside of the sphere. A solid disk is different from a hollow tube in that the solid disk is solid throughout the object, with no space inside. All of our k coefficient values were found on the website dev.physicslab.org. Our original values were the same, and we found them from our Physics 1 class. Our experiment involves the law of conservation of energy and looks into the coefficient of moments of inertia. We looked at the conservation of energy equation and came to the conclusion that we needed to design an experiment to measure the final velocity v of the object rolling down the incline, as well as recording the height at which the object is released. We kept the height constant for all trials to minimize the number of trials and therefore the number of calculations. 2 and g, or the force of gravity, are actual constants in our equation. H is the controlled variable at which we decide whether or not, or we decide what point to release the object. V is the independent variable as it is measured by the motion sensor, and k is the dependent variable as it is dependent on this value. The h would be measured with a ruler, the v would be measured with a motion sensor, and the k would be measured by actually inputting our values for h and v, or height and velocity, into our original equation and finding out the coefficient of inertia, of a moment of inertia. This is our discussion. An important substitution is made in our conservation of energy equation, where we set v, velocity, is equal to rw. Here is an explanation of that substitution. We start out with the original equation, theta equals s over r, where s is equal to the arc length in meters, theta is equal to the central angle in radians, and r is equal to the length of the radius in meters. Then we divide by time, theta over time, as well as s over rt, and we end up with w is equal to v over r. A simple movement of the r to the other side, and we get wr is equal to v, or angular velocity times the radius equals linear velocity. I also use dimensional analysis to check my work, as shown here. So I put the theta in its radians, s or arc length in meters, and the radius in meters. So this is the exact same setup as this, except in different units. Then I divided by time, or seconds, here, so radians over second, as well as meters over second meters. So we end up with radians per second is equal to meters per second times 1 over meter. I split these up to highlight that radians per second is actually equal to the angular velocity, as well as the meters per second is equal to the linear velocity. And then the simple movement of, I put these back into their original form, w equals v over r, and then simply multiplied the r to both sides and ended up with v equals rw, which is the exact same derivation as we reached over here. Our derivation was verified by the free knowledge website allenpedia.com. Allenpedia.com divided by time and portrayed the correct units for angular velocity, which is radians over time, as well as linear velocity, meters over time. The radius was not affected by the division of time because it was already underneath the arc length s.
The hypothesis for our experiment was the following. If the k values we determined through our experiment are equal to the k coefficients provided on the website dev.physicslab.org, then the k coefficients we have been provided with can be deemed accurate. The materials for our project were the following. The Vernier Logger Pro program with LabQuest 2 connected science system to gather data from the Vernier Logger Pro program. A motion detector that is compatible with the Vernier Logger Pro program. A wooden hollow tube, a tennis ball, a wooden solid cylinder, a meter stick, a wooden incline, and a makeshift barrier. We used a backpack to stop the ball from rolling across the classroom. The procedures for our lab were the following. Step 1. Insert LabQuest 2 connected science systems wires into the motion sensor and plug power box into an outlet. Step 2. Place motion detector at the top of the wooden incline. Step 3. Place your makeshift barrier about 1 foot from the bottom of the ramp to prevent the object from rolling across the classroom. Step 4. Place object at top of wooden incline directly in front of the motion sensor. Angle the motion sensor so that the middle of the motion sensor is directly across from the middle of the object. Step 5. Check to ensure the portable LabQuest 2 connected science system is running and displaying the correct graphs by conducting multiple practice trials. Step 6. Measure and record the height in centimeters of where the first object is released from. For optimal results, we recommend using the same height for each trial to avoid variation and human error. 7. Press Collect button on LabQuest 2 connected science system. Step 8. Release the object and allow the object to roll down the ramp and hit the makeshift barrier. Step 9. Press the Stop button on the LabQuest 2 connected science system. Step 10. Record the maximum velocity found on the velocity graph in the LabQuest 2 Connected Science system into the data table. The maximum velocity should be the highest point on the velocity versus time graph that is displayed on the LabQuest 2 Connected Science system. Step 11. Repeat steps 4 through 10 until you have 3 different trials for each object. Step 12. Complete steps 4 through 11 for 3 different objects.
So it's percent error because we're gonna have to figure that out.
Okay, so what we did was we took gravitational potential energy and set it equal to transitional kinetic energy and rotational kinetic energy. So in the rotational kinetic energy, we substituted kmr squared because we wanted to solve for k, and we canceled out the r squareds. We canceled out all the m's, and we got the 2gh equals v squared plus kv squared. Then we did some extra math, and we got it down to 2gh over v squared minus 1 equals k. And we plugged it in, and we got 1.5. And then we did the percent error calculations and got 50% error. Okay, so what we did was to try and figure out what our sources of error were. We figured there was a lot of friction because there's a lot of error, so we figured friction would correct that. So when we figured that friction would come from bumping along the sides, so what we did was we took the equation we had before, mgh was 1/2 mv squared plus I omega squared, and then we added friction, which is friction times distance. So then we substituted the known k value because we want to do substitution to figure out how much friction there was. So we did substitution. We plugged in the values we got and the known k, and then we got 1.4 joules of friction. So we thought, well, how do we know if there actually was friction? So we figured that like if it was bumping, you wouldn't get the full amount of friction. And by full amount, I mean if it just slid down. So then we calculated to see how much the friction there would have been if it just slid, and it was less. So that's how we were able to conclude that it bumped, and that was the biggest source of error. And also the way we found the coefficient of friction was through sliding it up and through changing the angle to see when it slid, and that was how we found that. So yes, that was a biggest source of error with bumping along the sides. So what we can conclude from this is that you actually can determine the k value experimentally through rolling body down an inclined plane. Even though we had trouble with the Vermeer Logger Pro system, trouble with accurate measurements, and trouble with bumping, we still feel this would work. We should limit all the error, then it should work.